Yeah. So we were talking about, so before in the previous session we talked about perfect zero knowledge. We saw a couple of different protocols that achieve this property, and we talked about the stronger version of this property and so on. And so now I want to take this property, and like I was saying earlier, right, the definition, for a definition to be useful, it has to capture something meaningful, a meaningful security property in this case, and it also has to be realizable, meaning that you need to have things that satisfy the definition, because otherwise what's the point of having the definition. So in this case, after these relaxations over here, this is a meaningful definition in the sense that we saw some interesting protocols that satisfy this definition, and it's a meaningful security property. But it still turns out to be somewhat limited. Like the set of languages that have the set of promise problems that have protocols that satisfy completeness and soundness and perfect zero knowledge is still somewhat limited. Like based on certain beliefs we have from complexity theory, we believe, for example, that the so-called NP-complete problems cannot have these kinds of protocols. Like, for example, if I gave you some Boolean circuit and I asked you whether there is some input for which it outputs 1 or something like this, these kinds of problems which come up regularly in various settings, we believe that they will not have perfect zero knowledge protocols, right? And so what is found to be really useful, what has been found to be really useful is a certain relaxation of this property, of the perfect zero knowledge property, to ask for the zero knowledge property that is only computational rather than perfect, right? And thereby it relaxes this what you're asking of the protocol. So I'm going to write down the definition, and then we'll talk a bit about what this means. So with perfect zero knowledge, we said for every possible cheating, every possible verifying algorithm, there is some simulator, some efficient simulator that can exactly simulate the view of that verifier. Yeah. So this thing, yeah, you can define that class, and we know some things like it is contained in. If you know these classes, you know it's contained in like AM and co-AM, something like that. So it's somewhat pretty low in the hierarchy. But we would like to do more. We would like to ideally get zero knowledge proofs in some sense for a much wider range of problems, right? And to do that, it helps to relax the definition of zero knowledge to something that is still something that is weaker, so that it's more achievable for a wider range of languages, but that is still strong enough that it represents meaningful security, right? And one very useful relaxation that we know of is a computational relaxation of this property. Where what I'm going to ask is, I'm still going to say that I want some security for every possible efficient verifier algorithm. So I will still want to say for every polynomial time V star, there is some polynomial time simulator, and I still want this. I still want a simulation guarantee for every yes instance. But now, instead of asking that the simulator simulates the view of the verifier in the protocol perfectly, I'm only going to ask that the simulator it produces some distribution that is computationally indistinguishable from the actual view of the verifier. Right? So instead, I'm going to say that if you give it this thing, this produces some distribution because it's a randomized algorithm. I'm only going to say, and this is the symbol I'm going to use, I'm going to say it is computationally indistinguishable from the distribution that is the view of this verifier when interacting with this prover. Right? And this concept you have seen before, right? In the past few days, the computational indistinguishability is fine. Okay. Yeah, so this is what I'm going to ask for. So this is weaker because at least, okay, if I put half over here, it's not clear which is stronger. But remember that this you can always amplify, right? You can just repeat this many times until the probability of failing goes down. So once you do that, this becomes a very clear weakening of this definition, because if the probability of failing is very, very small and the distribution you simulate when you don't fail is identical to the view, then by definition they are computationally indistinguishable. Right? That's one way of being computationally indistinguishable, is to be almost the same distribution. Right? But you don't have to be. Like these two distributions, in reality they could actually be very far. They could even have disjoint supports, but they may still be computationally indistinguishable. Right? So this is a much weaker property than asking for perfect indistinguishability, than asking that you simulate the distribution perfectly. Right? And this property you can achieve. You can get computational zero knowledge protocol for a much wider range of problems. But of course, when it comes to these kinds of computational constructions, you need this computational hardness from somewhere, right? Because as with some other things we talked about earlier, the tools we have in theoretical computer science are not developed enough to be able to prove very useful lower bounds. We cannot really prove that many languages which are useful are actually hard. So we often end up having to make assumptions about the hardness of various problems, and we have to end up having to make assumptions about the certain distributions being indistinguishable and so on. And so to achieve this property for in a non-trivial sense, meaning any problem that has a perfect zero knowledge proof also has a computational zero knowledge proof, because the same thing is computationally indistinguishable. But if you want to get constructions of computational zero knowledge proofs for problems outside this set of problems which have the perfect proofs, we often end up having to make certain kinds of assumptions. This is not something that we can quite prove. You cannot quite prove that you need certain assumptions to do this, but so far the only constructions we know is we need to assume something. We need some computational hardness from somewhere, right? And it also turns out that you don't actually need hardness that is that hard. Like for example, we know, for example, that if you have all you need is these one-way functions. Have you guys heard of one-way functions? Did someone cover it earlier? So what we can actually show is that if you have any one-way function, then this implies you can use a one-way function in some generic sense. We'll see a little bit about this later. Then you can have a computational zero knowledge proofs for any language in NP, for any promise problem that is in NP. Again, NP I haven't really quite defined it. It's essentially the set of problems that have these non-interactive proofs, non-interactive deterministic proofs, right? And one example of this is the graph isomorphism problem. That's a problem in NP. For that, we did not need any assumptions. We were able to construct a perfect zero knowledge proof directly. But if you had one-way functions, then you can actually construct computational zero knowledge proofs for any language in NP, right? And in fact, you can do something even more than this. You can also get the existence of one-way functions also implies that you can get computational zero knowledge proofs for any language that has an interactive proof at all, right? Which is quite remarkable, because for anything that does not have an interactive proof, you cannot get computational zero knowledge, of course. And what we know is that if you assume this very rather weak cryptographic object exists, which is one-way function, this is one of the weakest cryptographic objects, right? And these are sufficient to get these computational zero knowledge proofs for any language that could possibly have such a proof. For any language that has any kind of interactive proof at all, you can get computational zero knowledge proofs if you have this one-way functions. Yeah. Yes. So actually, let me do that later. Have you heard of, for example, did somebody cover like pseudo-random generators or pseudo-random functions and all? They are all equivalent to this. So you can just think of it as, for now, you can just think of it as if you have like a PRG or a PRF, and all of these are in essentially equivalent. The directions are not very efficient, but they're essentially equivalent things, equivalent kinds of hardness. So any of these you can use to get computational zero knowledge for NP and for any language in IP. Right? Which it's perhaps one should be surprised that you can get this for any language that has an interactive proof at all. But yeah, you can do it. It's very interesting. And what I'd like to show you some like not the entire proof of this thing, but but with like at least the important parts of this proof. It's not that hard to do, but I just don't want to get too much into the details of all the components of this proof. Right. So what I'm going to do is first I'm going to erase some of these things. What do I not need? I'll just erase these names here. Okay, so what we are going to do, what I want to show you is I'd like to show you a construction of these computational zero knowledge proofs for a couple of different NP complete languages. So there's a very quick introduction to what this means here. Okay, so I'm going to just use this space to do it. So this NP, which I have not properly defined, is a set of promise problems, or set of languages, right? So it's this set over there. This is NP, and within it contains all the languages that you can decide in polynomial time, which is called P for polynomial. But it contains potentially a lot of other languages as well. And among all these languages, there are a few languages that are the hardest among these NP languages, and hardest in a specific sense. So hardest means that if you have, and these are called NP complete languages, right? And what it means is that if you have an algorithm that solves any of these problems, then that will give you an algorithm to solve any other problem in this set, right? And it's actually a bit more specific than that. It's you can actually, what it actually means is that given you take any problem pi over here, if I give you an instance of this pi, you can take any language over some, let's call it pi prime over here, right? So for any language pi that's here and any pi prime over there, there is a reduction from pi to pi prime, meaning there is an algorithm that takes an instance of pi and outputs an instance of pi prime, such that if you start with the yes instance of pi, you end up with a yes instance of pi prime, and if you start with the no instance of pi, you end up with a no instance of pi prime, right? That's pretty much the definition of this NP complete set. Like any problem is NP complete if it has this property. If you can start with any pi in NP and you can reduce to that this way. Okay, so that's what it means. And what we are going to do, so because you have these kinds of reductions, it is actually sufficient to construct a computational zero knowledge proof for any one of the languages in this NP complete set. So if you construct it for any problem in that set, then that will immediately give you a computational zero knowledge proof for any problem in all of NP. Because what you can do is if you want a computational zero knowledge proof for pi, you just reduce it to pi prime and use the proof for pi prime. So the nice thing is computational zero knowledge sort of it is preserved by these reductions, across these reductions. So you can just reduce to that and use the proof for that. So all we need to do is to come up with a proof for some language, some problem in this set. Yeah. So by definition, it has to be efficient. Yeah. A language, this pi prime is NP complete if and only if for every pi over here there's an efficient reduction from pi to pi. That's the definition. So a pi prime is contained in this. The definition of this set is the pi primes for which there is a reduction from any pi. Yeah, so it's enough for me to design a protocol for one of these pi primes, so one problem in this set, right? And some of these problems are more convenient than others to design these protocols for. So we're going to work with some of them that are more convenient. So let's start with maybe let's start with the. This is simpler. Okay, let's start with the protocol for the 3 coloring problem. Okay, let me tell you what this problem is. So this is an NP-complete problem, and an instance of this problem is a graph. Okay, like it's some graph on n vertices. Right, on some n vertices, and the question here, the task is I give you this graph and I ask you whether it can be colored with 3 colors. So what does it mean? So a coloring of a graph is where you take, so you have a set of colors. Let's say you have some number k of colors, right? Like then the colors are just called 1, 2 up to k. And what you're supposed to do is you're supposed to color every vertex of this graph, right? And maybe you color one of these, a couple of these with 1, some of these are 2, some of these are 3, and so on, right? So any assignment like this, so where it for every vertex associated with color, like red, blue, green, whatever you want to call them, the names don't matter. And a coloring of a graph is considered valid if for every edge in the graph, the vertices on the edge have different colors. Right? For example, this coloring is not valid because there is a 1 here and there is a 1 here, and that's not valid because this edge has the same color on both sides, so it's not valid. But if I were to change this, how can I change this to make this valid? Yeah, I just change it to 3, right? Now this is a valid coloring because you take any edge, the vertices on it are different colored, right? And now a very basic question about this is if I give you a graph, what is the minimum number of colors you need to color the graph, right? Now a decision version of this problem is I give you the graph and I ask you, can this be colored with a certain number k of colors or not? Okay, and for some values of k this is easy. For example, if I set k equals 2, if I give you a graph and ask you, can you color this with 2 colors or not, then I think that's pretty easy to decide. Only like a very small kind of number of graphs can be colored with 3 colors, with 2 colors, right? Like cycles and paths and some simple trees and stuff like that. Yeah, you can do things like that. I think it has to be like bipartite essentially. Only bipartite graphs can be colored with 2 colors, right? But then as soon as you go to 3, if I give you a graph and I ask you, can you color this graph with 3 colors, then that we don't know how to decide. That problem is NP complete. So it's very hard to decide given a graph whether you can color it with 3 colors or not, right? And then there are some other interesting results about like if you have 4 colors, there's a much larger set of colors that you can definitely color and things like that, right? But with 3 colors, it's already very non-trivial to decide. And as I said, it's NP complete. So as we were saying earlier, it is sufficient if I can construct a computational zero knowledge proof for this. For this problem, where let me define it a bit more carefully. Here the S set is basically the graph such that this can be colored. Can be colored with 3 colors, right? And the no set is this where it cannot be colored with 3 colors. Like there's no coloring that is valid, no coloring with 3 colors that's going to be legal, right? So if I can, and this problem like this yes and this set and this no set is NP complete. So my objective now is to design a computational zero knowledge proof for this language, for this problem. Okay, and to do this, I am going to use a tool that is often very useful in designing zero knowledge proofs and interactive proofs more generally, and these are what are called commitments, cryptographic commitments or commitment schemes, right? Have any of you heard of these things? How many of you have heard of commitments? Okay, so let me talk about them anyway to get us all on the same page again. And I don't want to define these too formally because it can get a little bit hairy because there are some details. So I don't want to define this very formally. For now, just for the purpose of talking about these protocols, which again I'm not going to go into too much detail into the protocols in this session because it's already the evening, right? So I'm going to give you only like high level overviews of these protocols and we'll talk about how you simulate them and so on, but we're not going to go into too much detail, right? So at that level, I want to just talk about these commitments with a physical abstraction, right? So I can think of these commitments as these locked boxes, okay? So Imagine that you have like a physical box that you can lock and that has a key. That has this one key, okay, and it's an opaque box. So I have this box, I can put something inside the box and I can lock it and I can give it to you, right? Now what properties? I want to focus on two specific properties that this system has. Like when I give you this locked box with something inside. The first property is that if it is opaque and you did not see what I put in, you cannot see what is inside. You don't know what is inside. Like let's say I wrote something inside, I wrote some number inside and put it inside. You don't know what I have written, you don't know what is inside. And this property is called hiding. It's called the hiding property, which says that if I give you this commitment, which in this context you can think of a commitment as like some string, like some special kind of string that encodes some information, and it encodes this information in a way that if I don't give you this key that I have, you don't know what is inside the commitment. Like you don't know what's inside the box. And the other property is that once I have given you this box, I cannot change what is inside the box, right? Because you have the box, I don't have the box, right? So, and this property is called binding. Okay, binding in the sense that I am bound to what I placed inside the commitment, to what I placed inside the box. Okay, so commitment is basically a way to realize these two very intuitive properties that you have in the physical world in this digital setting, right? Where you have all these algorithms that do stuff. And maybe I'm going to abstract this out heavily. Okay, I'm not going to go into any detail at all. And the way I'm going to think of this is a commitment consists of let's say 2 algorithms. All right, I'm going to say it consists of 2 algorithms that I'm going to call commit and decommit. Commit, and what commit does is it takes some string that you want to commit to, or in this case, yeah, it takes some string, some message that you want to commit to, and it outputs 2 things. It outputs a commitment and it outputs some decommitting information. Okay, and then there is a let me call it a verification. It is sometimes called a decommitting procedure, and I am not involving keys or anything at all because again I don't want to go into too much detail here. So the process of the commit algorithm is to produce, like, think of the C as like the box and the D as the key. Okay, the C is a string that I can send to the other person to commit to M. So the C contains information about M and it's committed to. Once I give you the C, I am committed to the C. This M is what I am putting inside the C. And this D is information that will let you look inside the commitment. It's like the key in our analogy. Okay, and the way we think of it here is that given this commitment C and given this M and this D, this will either accept or reject. Meaning what it is doing is really it's checking whether this procedure is supposed to check whether the thing that was committed to by the string C is the M. And to do that, you take the key. So this is the box. This is what I am saying is inside the box, and this is the key. And you use the key to open the box and see whether M is in fact what is inside. Right. So this is the abstraction here. So it just accepts or rejects, meaning it's verifying that M was what was committed to. Right. And now I can again roughly state the hiding and binding properties over here. Hiding essentially says that if I only give you C, you have no idea what M is, and you don't know if you don't know the D, and C hides M. Let me give you just a little bit more detail. What I want to say is that for any M1 and M2, if you generate C1, D1 and C2, D2, imagine that's what you do, then what I'm saying is that the C1 is indistinguishable from C2. It's a stronger way of saying that the C hides M, right? But that's what I really want to say. I want to say that the C hides the M. This is the hiding property. And this indistinguishable, it could be statistical or computational. You get different kinds of commitments based on what exactly you ask for. But again, I don't want to go into that much detail right now. And this is the hiding property. And the binding property says that I cannot commit to one thing and later claim that I have something else, that I committed to something else, right? and I'm going to write down a very strong version of this property here. Typically, you may not be able to get this strong version of the property, but what I like to say is that for any C, there exists. I want to say for any C, I want to say there is only one M that I can decommit to successfully. Right? For any C, there exists at most one M. So let me write it that way. Exists one M for which there exists D such that the verifier accepts. Right, and this, you see why this is the binding property, right? I am saying once I have created this C, there is only one possible value of M for which I can give you a D that makes the verification pass. If I try to convince you that if I generate this C using this M, and then I later try to convince you that it's a different M, then I just won't be able to find the corresponding D that will make you believe that it's that M prime that I committed to. Because some of those may not be valid strings. Because I said for any C, like it could be any string. Yeah. Second. Mm-hmm. No, it's fine. It's fine if there is no M. That's okay. I'm okay with that. Yeah, this is a very strong version of the binding property. Typically, you won't get something so strong, but it's fine. Actually, you can get this in some cases, but right. But the main thing to keep in mind is the spirit of this, because typically they're not even. Usually, you need some interactive procedure to do this. Usually, it's not even just like an algorithm. But we're ignoring all that for now. Here, let's say it is. Yeah, let's say it is computation. Right. And that is where our computational general is going to come from. And these properties I'm going to use in the construction. So I'm going to use these commitments in my construction, and each of these properties I'm going to rely on to get different properties, different security properties of my protocol. To get my soundness and zero knowledge properties, I'm going to use these properties. And in fact, yeah, let me actually say that this is in fact computational, because we're talking about computational zero knowledge, and zero knowledge is going to come from here. And really, if you only want to rely on those, then you'll have to restrict yourself to some things here. Okay, and these things you can get some versions of these. Not maybe you have to change the definition a little bit. You can't write exactly this, but you can get these from any of these assumptions. You can construct objects like this from one-way functions, PRGs, or PRFs, and so on. Yeah. So how were you thinking of using it? So wait, you're saying that this C, you want to use a signature scheme? Okay. I see. So this is a you have encrypted this, and this is your secret key for the encryption scheme, and then you want to say, so it's not clear that you can do that, because maybe it's possible to come up with a different key that decrypts the ciphertext to something else. All right, so it's not clear that you get that property.
So we want exactly 1M, so for that 1M there can be multiple D also.
Yeah, I don't care. Yeah, it could be. Yeah, it could be.
And can't we have multiple M's for which different D's can?
Yeah, that's what I don't want. Yeah, that should not happen. Yeah, I want the M to be unique. The D I don't care. It can be many D's. Right. Alright, so imagine you have an object like this, okay? Like I said, in reality, it's a bit more complicated than this. You end up needing like an interactive protocol with a couple of rounds to get this. But let's say you have this. And now what we want to do is we want to use this to design a protocol for this 3 coloring problem. Right? So how can I do that? Any ideas for how we can do that? So first of all, it's easy to see that if you don't care about zero knowledge, then it's easy to get a protocol for 3 coloring, right? How would you do that if you did not care about zero knowledge? Yeah, I can just give you the coloring like I just showed you there, and you can verify that you can go edge by edge and make sure that the colors are different, right? Now, if you do want zero knowledge, what can you do?
Hide the information about getting to that isomorphism using.
You want to take an isomorphism. You want to take some random. So one difficulty with that is that the graph has a isomorphism problem, right? So to do this, you have to rely on, because you're relying on the hardness of the graph isomorphism problem to get zero knowledge. Because what are you doing? You're taking a graph, you're taking a random relabeling of this graph, and then you are actually revealing the coloring of that to the verifier. And now you are relying on the fact that it's hard to find this relabeling to hide the actual coloring on your actual graph, right? But the issue with this is that the graph isomorphism problem is hard, but it's not hard for all graphs. Like there could be some graphs where it's trivial to find the relabeling, and that would then reveal the coloring on the original graph that you have started with. So you need to do something else. What can you do? Mm-hmm.
Before querying, you comment it so that once you query, you can't change and you can randomly query whatever.
Yeah, this is the kind of thing we are going to do. So we are going to use, just to anticipate what we are going to see, right? You'll see that we are going to use the hiding property to get the zero knowledge property in our protocol, and the binding property to get the soundness property in our protocol. Okay. So what is the protocol going to be? We are going to essentially take some random coloring of this graph. So there is some coloring of this graph. You can randomize which colors are called what. Like you can randomize the names of the colors. And then we are going to commit to this coloring. Right? So imagine, let's take that graph itself, right? So, so there is the prover and the verifier. Let's take that particular graph. So you have right, and imagine you take that particular coloring, but let's say you randomly change the names of all the colors. It doesn't matter, right? It preserves the colorability property if you do that. So I'm going to call this, right? So I have this coloring of the graph where I randomly change the names of the colors. Now what I'm going to do is I'm going to commit to this coloring to the verifier, right? Using my commitment from over here. Meaning I'm going to take, for each vertex, I'm going to like put the name of this color in a box, right? And then I'm going to send all of these over to the verifier, right? I'm going to send all of these commitments to the verifier. So I'm just going to say, let me call it like this is C1, C2, this is just the C3, C4, C5, this is just the names of the commitments, right? So I will send the commitments to the colors to the verifier, right? And now at this point the prover is committed to this. So because of the binding property, the only value it can open each of these commitments to is the color that was actually inside that it committed to, right? It can't change that later. It's committed to this. But at the same time, the verifier does not know what is inside these commitments. It knows that the prover cannot change what is inside the commitments, but it doesn't know what is inside the commitment. And this is what we are going to use, right? And what the verifier is going to do is it wants to check that what was committed to is a valid coloring. because that's what the problem is about, right? You want to make sure that what you have is a valid coloring. And for that, it's going to ask the prover to open some of these commitments, to give it the decommitment information, to give it the keys for opening the commitment to some of these commitments, right? Because the problem is if it asks, if the verifier is given the keys to all of these commitments, then it can recover the entire coloring, which is information. You cannot possibly simulate that, right? That's too much information, so you don't want to reveal that. So but then the thing is that you don't have to look at the entire coloring to be sure that it's a valid coloring, right? Because if it is not a valid coloring, then there must be some edge that has the same color on both sides, right? And so what you are going to hope to do, ask the verifier, what you are going to do is you are going to pick a random edge in the graph and just check that edge, right? And you know that if it's not a valid coloring, at least one edge will be wrong, and there's going to be some probability that you will pick that edge and you will discover that it is not a valid coloring. Whereas if it is a valid coloring, then it doesn't matter what edge you pick, you are going to find that it's valid. Right? That's the idea. So all I will do is I will pick some u and v, which is some random edge in this graph, and I will send u and v, and the prover will reveal the opening information for just those vertices du and dv, and it will also tell me what the colors are, let's say. So it gives you these two things and it will tell me what the colors for these things are. I need to give those some names. Let's say too many numbers here. So let's say that the colors represent, so let's say that this is, I'm going to use M for the colors, keeping with the M over there. So the names of the colors are this, are M1, M2, M3, M4 and M5. Right? So the prover sends back the opening information along with the names of the colors, which it doesn't actually have to do because there are only like 3 possible colors, right? You can just try everything, but whatever. And then what the verifier is going to do is it's going to check 2 things. It's going to check that this mu and mv was in fact what was committed to in the commitments, right? So it is going to check that if you look at the commitment to the color of u, is it actually mu, and you will check that with you will do that for both m and v, and then finally you will make sure that mu is not equal to mv, because that means the coloring is valid, right? So you'll make sure, so you're getting, let's say you pick these 2, then you will get this M2 and M4, which is like, it will say the colors are 3 and 2, and it will give you the corresponding opening information, and you'll just make sure that the respective commitments do in fact have the 3 and the 2, and you'll check that 3 is not equal to 2, right? And by doing this, you have made sure that you have checked that the one edge that you opened is in fact validly colored, and beyond that you haven't really learned anything else, right? Because if you know that the graph is in fact 3 colorable, then you already know that any edge you pick is going to have different colors, right? And that's the only thing you learned here in this protocol. Assuming that the commitments are in fact hiding and everything, the only thing you learned in this protocol is the fact that the one edge that you saw has different colors on both sides. But if you knew that the graph is colorable, then you already know that this is the case, right? Because the names of the colors are also randomized, you are getting no other information. And this is why this protocol is zero knowledge. Like you have to design a simulator and everything, yeah. But this is the idea behind it. This is why this is the intuition behind designing the protocol, and this is also what you use to construct the simulator as well when you actually do it. Right? Then you just reject. If mu is equal to mv, then you say okay, there is no that you decide it's not colorable, because if the graph is colorable and the prover is acting honestly, that will never happen. So that mu can be equal to mv only if the prover is not acting honestly and the graph in fact is not colorable, not 3 colorable. That's the only situation where that can happen. So so if you look at the three properties, right? Let us again, let's go through all the three properties and make sure the protocol has all of them. So in the case of completeness, your graph is three colorable. The graph is three colorable and the prover will act honestly, right? It will actually take a valid three coloring, meaning that every edge will have different colors on both sides and it will do all these commitments, it will do everything honestly. So in that case, you will in fact pass all these checks because the prover can answer honestly what MU and MV was. It can actually tell you what it put inside the commitment and you will find that they are different because the prover started with a valid coloring, right? So everything will pass. So it's fine, right? So in this case, you can check like all of your checks will pass. If the prover acts honestly, which it is going to act honestly, right? Like why would it not act honestly? And for the soundness property, what we just said is that if the graph is not three colorable, then the prover has committed to something, right? So each of these commitments, there is only one possible value that is inside that commitment, right? Now, and if you think about that set of values, there is some M1 to M5 that is actually inside the commitment. If you think about those, the verifier doesn't know them, but they exist, right? Now think about that set of values that is giving you some coloring of this graph. But if the graph is not three colorable, then it cannot be a valid coloring. And that's the point. If it's not a valid coloring, then there has to be some edge on which the colors are equal. Right? So if G is not three colorable, then if you look at then this M1 up to M5 is not a valid coloring. Or let me just call it Mn in general. It's not a valid coloring. Which implies that there is some UV such that Mu is equal to MV. Mu is equal to MV, right? And with some probability you will pick this UV, right? So the probability that this U comma V is sent by the verifier, because the verifier is sending this one edge, right? Sent by this V is essentially equal to 1 over the number of edges here. So with at least this probability, you will actually ask for an edge that is not colored properly by the coloring that the prover committed to. So the prover is committing to some coloring. There doesn't exist a valid coloring, so the coloring that the prover is committing to is not valid, which means that on some edge the colors are the same. So with some probability you will ask for that edge, and the prover can't change its mind anymore because the commitment is binding. It cannot give you some MU and MV that are different from what was committed to. Right? And this is really the power that the commitments give you. They enable the prover to fully commit to some information without revealing that information, so that you can reveal the information later on, and the prover cannot change its mind about what it's revealing based on what the verifier is asking it for. Right? So these commitments are very useful. They are very powerful because for this reason, that the prover cannot change its mind. At the same time, it isn't actually revealing the information. Yeah. So here the soundness is quite bad because the protocol may still accept with probability 1 minus 1 over E. So you have to repeat and make this smaller. So you end up having to repeat this sequentially, but it will only be some polynomial number of times. You have to repeat it, I think, the number of edges number of times, and that will become some constant if you do that.
What if the cheating prover just does a two coloring? So like you don't kind of get this edge, but maybe you have to query all edges to find out.
No, so if there's no three coloring, that means there's no two coloring either. Yeah, there's so if you're, and we have agreed on what names we are using for the colors. We have agreed there can only be 1, 2 or 3. So if Mu is 4, I will immediately reject anyway. Right. So you only have 3 colors and you have to color them, but you cannot. So you have to do something invalid. Right, and And yeah, zero knowledge comes from, let me, so your computational zero knowledge comes from the fact that the commitments are hiding. And if you want to simulate this, the commitments essentially, because of this, right, it doesn't matter what you're committing to, the commitments are computationally indistinguishable. So inside these things, when you're simulating it, you can put whatever you want, and it's going to look the same, right? So knowing this, how would you simulate this protocol? Like how would you design a simulator for? Think about just the honest verifier for now. How would you simulate this protocol? How would you design a simulator for this protocol?
So don't
First pick a random UR comma V,
Mm-hmm.
assign them colors, then give any colors to the rest of the nodes and commit it and give the corresponding
Yeah, this is pretty much what you would do. You would have the same advantage. So in all of the cases we have seen so far, right? If you compare what abilities the prover has and what abilities the simulator has, the prover is computationally unbounded, which the simulator is not, right? So that is an advantage the prover has. But the thing with the simulator is it has access to information in a different order from which the prover has access. The simulator can decide what the verifier's second message is before deciding what the prover's first message has to be, which is not something the prover can do. The prover initially has to send something, committing itself to something. But here the simulator can first pick what this u comma v is going to be, and then it can commit to things accordingly, right? So the simulator can simply do the following. So the simulator for the honest, this is the honest verifier. You can also do it for the malicious verifiers. It's just a bit more complicated, but the same principle as these things you can use. So what you would do is you would pick a random edge, and then you would come up with commitments. There's some CU and some CV, and you come up with, you commit to this n colors such that you can actually put, it doesn't even matter what you put in the other places. You can put just one everywhere else, except for these two you just pick some two different colors. Doesn't even matter what the colors are. Let's say like 2 and 3, you just commit to two different colors just for that edge, right? And then you also end up with the corresponding decommitting information, du, dv, dn, and now you can just you just output the relevant pieces of this because you will just output. So you will output the first message is C1 to Cn, and then the second message is U and V, and the last message is you output, in this case it will be this 2 and 3, right? This 2 and 3 along with du and dv. Right? And then you can show that by the hiding property of the commitment, this part, so everything else is identical to the actual protocol. It's only this set of commitments that is different. Otherwise, it's exactly the same. But you can use the hiding property of the commitment to show that this part, this set of commitments, is computationally indistinguishable from the actual commitments to the actual valid coloring. So this is not a valid coloring at all, right? This where I put ones everywhere else and just different colors in my edge. This is not a valid coloring because most of the edges have the same color, have one on both sides, right? But the commitments to this coloring is indistinguishable from the commitments to a valid coloring. It's computationally indistinguishable by the hiding property of the commitment. Right? That's how you argue that this is computational zero knowledge. Yeah.
if C1, C2 are both 1, then
Mhm.
does that satisfy the binding property?
Uh,
For all C, it should just be 1 M.
yes, but for one M there can be many differences.
So, but can you verify like eventually figure out all the colors and just keep changing the permutation?
Yeah, you do have to keep changing it. Like every time you repeat it, you need to pick a new names for all the colors. You have to randomly change the names of the colors and then keep doing this. Do it over.
That computation becomes part of the simulator.
No, because only the prover sees that. Nobody else sees that. Yeah, so it's not part of the simulator, and that's important that the verifier does not see this. Otherwise, like you say, it can actually figure out like what the coloring is by putting together all the different parts. And this is sort of this is in some sense similar to the protocol here, right? Here there were these two pieces of information, the R0 and R1, that if you had both pieces of information, you can put it together into some meaningful information about the instance. Like here, if you knew both R0 and R1, you could have put it together to get the R hat, which is non-trivial meaningful information, right? Similarly here, if you had the colors of all the edges, you can put it together into the coloring of the entire graph. The colors of all the vertices, you can put it together to get the coloring of the entire graph. But then the key thing is that we are only revealing parts of the information to the verifier. So here, you never reveal both R0 and R1 together to the verifier, you reveal just one of them, right? Similarly here, you never reveal the colors of all the vertices at the same time to the verifier. You only reveal like one pair of vertices at a time, which is still not enough for the verifier to learn anything. Right, and this is a protocol. This is essentially the entire protocol. You just need to figure out how to construct these commitments, and the commitments, like I was saying earlier, often they end up being interactive. So it's not this simple, but this is the essence of the protocol. This is all you really need to do. Right, everything else is details.
Commitments come from one-way.
Yeah, you can get them from one-way functions or from pseudo-random generators. It's somewhat straightforward to get one construction. There are many different constructions, but it's not that hard to get them. Okay, so in the half an hour that we have left, what can we do? I can tell you a couple of things very quickly. I can show you, no, it's not really worth showing that. Okay, let me just tell you about how you can go from, so far, this gives us this, right? It gives us the computational generalized proof of NP, because you can start from any promise problem in NP, reduce it to 3 coloring, and then you can run this protocol, and that will give you a computational zero knowledge proof for that problem, right? But how do we go beyond this? How do we get to computational zero knowledge proofs for all of IP? So it turns out that actually needs a few more tricks to get to. So you need a couple of steps to get there, and the first step there is to take your interactive proof. So what do I want to do now? Now I have some problem for which I have an interactive proof. Okay, it's like a fully interactive proof, not just NP. It's interactive. It has randomness, everything. It has many rounds. It could have like a polynomial number of rounds of interaction, right? Now, and I want to get a computational zero knowledge proof for this problem. I want to somehow take this protocol and use it to design a computational zero knowledge proof. And I'm going to go through a couple of steps to do this. So the first thing I'm going to do is I'm going to make sure that this protocol has some additional structure, right? So in general, what do these protocols look like? So there's the prover and the verifier, and there's some interaction of messages, right? Let me call them. So the verifier sends some message alpha 1, and the prover sends some beta 1, and so on. And let's say there are some R rounds of interaction. So there's some beta R, and at the end of which the verifier will just either accept or reject, right, based on all of this information, and there's the instance as well. This is what a general interactive proof looks like, and there is some randomness that the verifier has. There's some private randomness the verifier has, right? Now what I'm going to do, the first step towards getting what I want is I'm going to take this protocol and convert it into a protocol where the verifier's messages are all uniformly random strings. Okay, so I want it to look like this instead. So I want to take this thing. So here, the important thing here is that between these rounds of interactions, the verifier could be doing some arbitrary efficient computations, right? Like this alpha 1, what is its dependence on x and r? It could be anything. All I know is it is efficiently computable, that's all I know. But beyond that, it could be anything. Similarly, given the alpha 1 and beta 1, what is alpha 2? I don't know, it could be anything. It's some efficiently computable function of x, r, alpha 1 and beta 1. Beyond that, it could be anything, I don't know. Right? All I know is this is some interactive proof. Right? But what I'm going to do is I would like to change this protocol into one that has the following structure, where every message of the verifier is in fact a completely random string that is independent of anything it has seen so far. Okay, so this is going to be some R1, where R1 is sampled from some length. So it's a random string of some length. The length may change, but for every round I send a random string of some length, and then the prover can send whatever it wants, can do some processing of this, it sends some beta 1, and the next thing the verifier does is it doesn't even look at the beta 1, okay, it doesn't look at the beta 1, doesn't look at the x or anything, it just samples another string of length some L2 and sends this R2, and the prover responds with some beta 2 and so on, and this is what it does for all the rounds. So I'm using R for both number of rounds and this, but yeah. And then only at the very end does the verifier look at the entire transcript so far. It looks at all of the Ri's and the beta i's so far and the x, and then it decides whether to accept or reject. The idea is that until this point, the verifier has not done any processing at all. All it does is it samples a new random string and sends it to the prover. Right? And for soundness, we are going to rely on the fact that the prover doesn't know what the next string is going to be. Right? It has to send this beta 1 without knowing what R2 is going to be. That's going to be the only source of our soundness. Right? And it's not completely unimaginable that you can do this, because if you look at this protocol, for example, has this structure. Right? While the prover sends some message, but the verifier doesn't even look at this. Right? It just samples a uniformly random bit and sends that. And then the prover sends something else, and then at the end, the verifier processes everything it has seen so far. Right? So it's not fully unimaginable that you may be able to do this, but it's not easy to do. That it needs some work, but you can in fact show that you can take any interactive proof that looks like this, and you can transform it into an interactive proof for the same problem that looks like that. Yeah.
In this case, then why do we need rounds at all? Can't we send all the R string with one?
No, because what you are really relying on is the fact that the prover is setting this beta 1 before it knows the R2. Like here, for example, if the verifier had sent the B beforehand, then you have no soundness. Right? So it really matters that there is this ordering, that the prover says something before it knows what the verifier is going to say next. That's the only thing we have left here. There's nothing else left here. That's hard for the prover, right? This is the only source of soundness in this case. And it turns out that I don't have time to go into this, unfortunately. It's a very nice protocol that you can use to go from here to here. But you can take any protocol that looks like this, and you can transform it into a protocol that looks like this without even too much cost. Like I think you only need to increase the number of rounds by 1 or something like this, 1 or 2 or something like that. You need like 1 additional round, but other than that, you can basically do essentially this. Right? It's a very nice transformation. And again, there will be, like, if you look at my web page and look at the notes and all, there will be references for all of this. It's very simple also. It's a very simple transformation. It's very useful in other aspects as well. But yeah, so this is the first thing I'm going to do. Okay, the first thing I'm going to do is I'm going to take my interactive proof I have for some language that I am interested in, for some pi, let's say, and I'm going to transform it to look this way. And now I'm ready to do some things. So now, does anyone have any idea of what you could do? Like given that, let's say you have a interactive proof that looks like this, okay? And let's say I tell you that I give you a computational zero knowledge proof for any language in NP. Right? I give you this for any language in NP. And in particular, you have a computational zero knowledge proof for verifying any sort of computation, because that is one of the things in NP where I tell you that, okay, here is the circuit, here is the input and here is the output. If I give you these things, then verifying that the circuit actually produces the output with this input, that's an NP statement. Like the fact that the circuit produces this output is an NP statement. So you also have a computational zero knowledge proof for that. Right? Knowing these things, can you think of? Actually, it's a bit annoying. It's not very direct, but does anyone have any ideas of what you could possibly do?
First, by generating all the R1s initially
Mm-hmm.
for simulation, and then going backwards, we can choose values of beta such that they fix in line.
So this protocol on its own is not going to be zero knowledge. It's just some protocol. So far, and the only property you know is that the verifiers messages look like this. I want to do something with it. I want to use this protocol to construct a zero knowledge protocol.
So then the prover can give a with this thing computational zero knowledge proof for knowing beta 1
Mm-hmm.
using that commitments and for beta 2 as well and till beta n.
Mm-hmm.
And then when the verifier needs to know if it actually knows beta 1, beta 2, beta n, then it can at the end give the decrypting information.
Yeah, this is the sort of thing we are going to do. So, what is the one thing that would have been simple if it was possible to do is what someone was saying earlier, where imagine you take all of the these RIs, right, all the random strings. So imagine you send them all at the beginning, and then the prover sends all the betas together. So in that case, it's not that hard to show that. Like imagine this, okay? So imagine it was possible to do that, where the verifier sends all the R1 up to the R, let's say, and the prover sends the beta 1 up to beta R, and imagine this protocol was sound, right? The problem with this protocol is it is not sound, right? Because if the prover knows all of the RIs, it can come up with things that are bad, like just like what you can do here. Like you can cheat very easily. But if it was sound, then it's not. Then you can turn it into a zero knowledge proof by doing the following. So what you can do is, I have all the beta i's, and I don't want to reveal the beta i's to the verifier, right? Because these beta i's, they have some information, because it's communication from the prover to the verifier. I don't know any other properties of it, so it may be revealing some information. So I would like to hide the beta i's from the verifier. So what I can do instead is, instead of sending the beta i's directly, I will just send commitments to these beta i's. So I will send commitments to, let's say, all of the bits in. I will send commitments to all of these. These are all strings, right? So I will send commitments to all of them, and then I will prove to the verifier that I know a set of beta 1 to beta R and D1 to DR, which is the decommitting information, such that with that information, if you open this commitment and you run the verifier's accepting procedure, the final decision procedure, it will accept. Right? Because what is the verifier going to do in the end? So over here, what is the verifier doing, right? There is some algorithm that takes as input the X, the R1, beta 1, R2, beta 2, and so on. So it takes all of these things and then decides whether to accept or reject. That's what's happening at the end of this protocol, right? So all the prover needs to do is prove that there is some beta 1 to beta R that satisfies, for which if you run this algorithm, it will output accept, right? So that's what it's going to do. It's going to prove that with a computational zero knowledge proof that there exists some beta 1 to beta R such that it satisfies the commitment, such that it satisfies such that what's the right term? Let me say satisfies the commitment, and if you give it to the verifier along with the R1 to RR and the beta 1 to the beta R, this accepts, right? And then the nice thing is, this is an NP statement. So this statement that there exists a beta 1 to beta R satisfying these properties, it happens to be an NP statement. Okay, I also have to include the D1 to DR. Now this is an NP statement because you can verify this efficiently. And if it is an NP statement, then you can use the computational zero knowledge proof from before to prove this with the computational zero knowledge proof. And then you can put it together with the hiding property of this commitment to say that in the whole protocol nothing is revealed. Because I did not reveal this beta 1 to beta r to you, and then I proved some statement about the beta 1 to beta r using a zero knowledge proof, meaning I still did not reveal the beta 1 to beta r to you. Right? So you really haven't seen anything. All you have seen is a commitment which is hiding and a zero knowledge proof which is zero knowledge also. And then you can prove that this whole thing is zero knowledge. Right? Of course, the problem with doing it this way is it's not sound, because if the prover knows everything in the beginning, it's not sound anymore. But you don't actually have to do this. You can do the same thing over here. You can just say, it doesn't have to be non-interactive like this. Instead, I can say the prover will receive the R1 and it will just send a commitment to B1. And here it is important that the protocol is public coin, because the verifier cannot see what is inside this commitment, but it doesn't need to, because the second message is just a completely random string. So it can sample this without looking inside this commitment, and it sends that. And then in response, the prover sends the commitment to B2 again, beta 2 again, and this keeps going on, and until the end I only send commitments to the messages that I want to send you. I want to send you some message, but I only send you a commitment to that message. But because it is a valid commitment, because it's a binding commitment, I cannot change my mind later on what the beta i's are. So it preserves the soundness property of the protocol, because I cannot change my mind on what beta 1 is based on R2, right? So it preserves the soundness of the protocol, and then at the end I can do the same thing. I'm using a hiding commitment, so it doesn't reveal anything until this point, and then I will do a computational zero knowledge, so proving exactly the same thing, which is zero knowledge. And so you can put all of this together. Again, there are some details to work out here, but really this is the entire idea. This is the high level idea of how you can get this. From here to there, yeah, that needs some effort. So if you're interested, look up. So this was done by Goldwasser and Sipser using a very nice protocol to prove bounds on the sizes of sets. So there is this protocol called the Goldwasser-Sipser set lower bound protocol. It's a nice. It has some very useful ideas. So if you're interested, I would look up this thing. Right? And if I had another half an hour or 45 minutes, I would have gone into it, but it's already too late.
So could you state that statement for which we give a CZ-K proof?
Yes. So this is here. I'm going to state it more carefully over here. Okay. So let me give these things names. There is R1. This is now the transform protocol. There's R1 that the verifier sends, and I'm going to send commitments to the beta i's. I'm going to call them CI's. Okay, C1 is the commitment to the beta 1, where beta 1 is the message the prover would have sent normally. Similarly, C2 is commitment to beta 2 and so on, and CR is the commitment to beta R, whatever. Forget the R plus 1 minus 1, whatever. So these are the commitments I'm sending throughout the protocol. And in the end, I am going to give you a CZK proof, zero knowledge proof for the following statement. So the way we have been talking about is in terms of promise problems in languages, right? So in that sense, I would be thinking of the following language. So there is C1 to, so this is a language that is defined by the instance X and the R1 to and the random values Ri's. Okay, so I am going to define my set of S instances. It is parameterized by the instance X that we originally had, that we are trying to do the entire protocol for, and the messages sent by the verifier, the R1, R2 and so on. So this is going to be a parameter in defining our language. We are going to define a promise problem using this. So fix the X and R1 to R, and now we are going to define the language. You can think of it differently actually, but actually give me a second. No, let's define it this way. And this is going to consist of strings C1 to CR, such that basically like these are going to correspond to those things, such that there exists a beta 1 to beta R and a D1 to DR, such that for every I the verification passes. So that if that such that the beta I is what is inside the CI beta I DI is accepting, and if you run the verifier algorithm with these as the verifier messages, like the algorithm at the end of this protocol, right? At the end of this public coin protocol, what is happening? There is an algorithm that looks at the entire transcript so far and decides whether to accept or reject. So you take that algorithm and you run it on the X and the Ri specified here. So and these beta i's. So R1, beta 1, R2, beta 2, and so on, and this also accepts. Right? So again, my language and the no instances are everything that is not this. Okay, yes instances of this, no instance is the complement of this. Okay, so I have defined now a promise problem where we are basically with this. So the yes instances are commitments such that if you look at what is inside those commitments, effectively, if you look at what is inside those commitments, they are valid prover messages that will make the verifier accept. That is the language over here, and then this is an NP language, because once I give you these, this is like an NP proof. This is like an NP witness, NP proof, a non-deterministic proof that something belongs in this language, right? So this is an NP language, and now you have a computational zero knowledge proof for this NP language, and that's what you will use.
So does X belong in Y is an NP problem?
Yeah. This is if I define it this way, this is an NP problem. So in practice, people, you won't actually do this. You would, if you want to get a computational zero knowledge proof for some specific problem that you care about, you won't go this route. You won't try to reduce it to 3 coloring and get a protocol for 3 coloring, because there's going to be some overhead. Typically, if your language is structured enough, you would try to come up with a protocol specific to your problem that is potentially more efficient than going through the reduction to 3 coloring and so on, which can blow up the size of your instances a lot. But in terms of showing what is possible, then this you can do. Okay, so I think this is a good place to stop. Any other last questions about any of this? Yeah.
Is it not enough to say for all C component
Mm-hmm.
one message and such that verify CFD?
You want to say for every CND there is at most one M. So that's a problem, because imagine what I do is let's say there is some C for which there are 2 different values of M, for which there are 2 different Ds that check out as valid commitments, right? That's a problem, because the property I want my commitment to have is that once I give you the commitment, I should not be able to change my mind about what is inside the commitment. So if I commit to some M, I should not be able to later tell you that what is inside is some M prime. That is different. So
Why don't we just give out the D as well at the same time?
because that might break the hiding property.
Yeah, so you will just give away the 3 coloring.
Yeah, that will break the hiding property. That's why you don't want to give out the D. Because you can just try, in this case, like there are only 3 possible values of M, right? So if you knew the D, you can just try all of them and see which one accepts.
So then after you get the D, won't it break the hiding property?
It would, but then you're only giving the D for that one edge, for which you're okay with revealing the thing anyway.
It breaks only because you could brute force it, or it breaks in general?
In general, I don't know, but in this case, I can actually, in this protocol, I'm also giving you what is inside, that's fine. In general, I don't know. But at least the commitment doesn't guarantee any properties at that point. So it may just reveal it at the time. Okay, anything else? Okay, then yeah, I guess we'll call it here. And good luck with the protocols, with the protocol lectures tomorrow. I think Pratyay is going to talk about certain specific kinds of zero knowledge protocols, among other things. So hopefully this will be useful tomorrow. Yeah.